Yes, children. Now, in the previous lecture, I was telling you about how alpha D glucose and beta D glucose are formed. Okay, this is by internal cyclization. The hydrogen from the fifth carbon of OH group, it is shifting towards the carbonyl oxygen and it is becoming an OH. Okay, so this is what we saw, right? And you're getting a hemiacetal form of glucose, and the position of OH, if it is to the right or if it is to the left of the first carbon, decides whether it is alpha form or beta form. This we saw it. Okay. Now, the two cyclic hemiacetal forms of glucose, where do they differ? They differ in the position of OH group at C1. Is it not? Now, what is that C1 position, that carbonyl carbon? What is it called? It is called anomeric carbon. Okay, what is anomeric carbon? It is the aldehyde carbon before cyclization. Okay, that is called as anomeric carbon. Okay, now such isomers which differ in the configuration of OH group at the anomeric carbon are called anomers, or you can say they are two stereoisomers which differ in the position of OH group at C1 position. Okay, they are called anomers. Now they are called as alpha D glucose and beta D glucose. These are the anomers of glucose. This is a very important question. Name the anomers of glucose. They can ask you in the paper, or a simple 1 mark question also. Okay. Now we saw the open chain में हमने cyclic structure देखा था, है ना? Now if you put it in the form of a hexagon, it is resembling that of a heterocyclic organic compound which is called pyran. This is called as pyran, having a double bond at the opposite ends. This is a hexagonal structure having one oxygen, right? So it is heterocyclic. If it was all carbon, then you call it as homocyclic. Since there is more than one atom, carbon के साथ oxygen भी है, so it is a heterocyclic compound, and this is called as pyran. Now, when you put the structure of glucose in that hexagonal form, that is also attached through oxygen, is it not? You are having like this. Okay. Now this is the oxygen. Then this is your C1, C2, C3, C4, C5 and C6. The last one. Okay. And this structure, that is oxygen के साथ 5 carbon, it is similar to that of pyran structure. Of course, no double bond and all is there, right? So we are calling this as alpha D glucopyranose and beta D glucopyranose, we call it. Okay, you can also call it as alpha D glucose and beta D glucose, no problem. Now, when you write the structure, this structure, if it is put along with hydrogen and OH which is attached to each and every carbon, then whatever is there on the left hand side you put above the plane, and whatever is there on the right hand side you put them below the plane, is it not? Now try to recollect your memory how you wrote it. See, 4, 5, 6, right? Then this was connected through oxygen, right? Then you have HOH, then again HOH, then third from the top, the hydrogen and OH, they are interchanged. Always remember that. Okay. So you have whatever is there on the right hand side, they are all put below the plane. This OH, then this OH, और इसमें OH इस side है, तो ये ऊपर आ गया. Again here it is on the right hand side, so it is below the plane. And then this CH2OH, it is above the plane, and hydrogen below the plane. Is that clear? So this is the pyranose form of glucose. Now if you take beta D glucose, only this will change. See, here it is HOH and here it is OHH. Except this, nothing else change, is it not? So only this configuration will differ in beta D glucose. Okay. Now both have different optical rotation values. That is, they rotate the plane of polarization of light at different angles. Okay. Now, this alpha D glucose, it is having an optical rotation of plus 111 degrees. And if you put this, alpha D glucose in water, what happens? Slowly it changes from plus 11 to plus 52.5. It comes to an equilibrium form, and this equilibrium form is showing an optical rotation of 52.5. Same way, you start with beta D glucose and you put it in water. This is having an optical rotation of plus 19.2, and this will also come to equilibrium form. So it will increase from 19.2 to 52.5. If you put alpha D glucose, it will decrease from 111 to 52.5. Okay. So you find this specific rotation of an aqueous solution of alpha D glucose. It falls from 111 to 52.5 with time, and that of beta D glucose, it increases from 19.2 to 52.5 again with time. So this spontaneous change in optical rotation, you started with alpha D glucose, you put it in water, is it not? And automatically the optical rotation power changed from 111 to 52.5. So there is a spontaneous change in optical rotation of an optically active compound with time to an equilibrium value is called mutarotation. Is that clear? So what is mutarotation, right? This is also an important feature, right?